Welcome to another exercise for the workbook Statistics. This time focusing on the topic of linear regression, or rather simple linear regression, the calculation of the coefficients of a regression line and the coefficient of determination. As an exercise, we have here a sample of Instagram posts is considered. For 5 randomly selected influencers, the followers in 100,000 y and the average number of new posts per month x are collected. By using regression analysis, the relation between the two variables should be studied in more detail. And we get this table here. That's actually the 5 different influences, and we have the follower numbers and we have the posts. So our task now is actually twofold. First off, we're going to build the linear regression line. That's a part here that describes the relation between the two variables. Then we're going to interpret the coefficients we just calculated earlier. And finally, we're going to calculate the coefficient of determination, the R-squared. So let's get right to it. I'm going to copy the table and I'm going to add first which is the x and which is the y variable. So what is the variable which is influenced or impacted, and which is the variable which actually does the influencing. So here we can assume that it's the post which drives the followers, or at least that's what I assume in the context of this exercise. There could be arguments that it's exactly the other way around. At this point, however, let's stick with the idea posts are driving follower numbers. So posts are x, the follower numbers are y. Then we're going to add 3 more rows. In the first row, we're going to put all the y values we have here in this row to the power of 2. So all of this to the power of 2. And then in the next row, we're going to do exactly the same for the x values, giving us those parts here. So that was just all these values squared. Then we're finally adding 1 more row where we multiply x and y values. So 20.7 times 14, 23.4 times 258, and so forth. That's more or less what we do in the first step for the calculation part. We're also going to add then a new column where we sum up all of the 5 different rows. That's just, however, an intermediate step, because what we actually need are the averages of the different variables. So we're going to divide all these 5 values by the 5 observations as well, giving us these 5 values. That's actually the only thing we need here, those 5 values. So if you do not want to, you could skip the whole column on the sums. You could also skip noting these values here and do all the calculation with the calculator alone. The important part, we need to get these 5 values, because in the context of the next, 2 exercises or parts, all of these values will be relevant in one way or another. Because if I start with A, with the coefficients of the regression line, I have the following formula for the slope. That's first off the average of x times y. It's actually the last value I calculated here, the 1607 point something. And then minus the average of x times the average of y, so 13 times 100, divided by what we have down here is nothing else than the variance of x, or the average of x squared, which here is the 18,214.8. So that's this average. And finally minus the average of x squared, so the 100 squared. If we put in the values, we get as a result 0.0374. Okay, so that's already the slope. Now we can use the following formula for the intercept, which is just the average of y, 13, minus b, that's this value here, times the average of x, the 100, giving us here an intercept of 9.256. Those two numbers then already make up our regression line. So here we have y is equal to 9.256 plus 0.0374 times x. And we can also interpret those variables. That's also our part B. But before we do this, let's add one more row to our table here, because we already have all the information we need and we're going to need this later on. This row will contain the y hat squared. Y hat, that's if I insert the x value into my regression line. So that's like my estimated y value. And I want to have the square of the estimated y value. So if I insert 14, I would calculate 14 times 0.0374 plus 9.256. Then there was only the y hat. I'm going to square the end result, giving me 95 point something. Then I'll continue. 258 times 2.2374 plus 9.256. Press enter, end result to the power of 2, giving me here 357.8, more or less. I'm going to do the same thing with the 137, with the 19, and with the 72. For all of these values, I'm also going to calculate the average, which here will turn out to be around 180. That's a value I'm going to need for the calculation of my measure of coefficient of determination. That's what I meant, the r squared. But well, we could also then continue with part B. What do the coefficients actually mean? Well, the slope parameter tells us if x increases by 1 unit, that's by how many units y increases. Well, here this would say 1 unit more of posts, this many more units of followers. But we have to take into account in which units are posts and followers measured. So if followers are in 100,000, I would have to multiply this first with 5 zeros, so move this 5 to the left to get a decent idea. So the 3 would be here. So I would have around 3,740 more followers per post. That would be more or less what I can make out of this. Also, if I would not post at all, meaning my posts would be 0, the x would be 0, then I can assume to still have, on average, this much followers. That's the intercept. The intercept can always be interpreted as if x is 0, then this will be the end result. If I'm not posting anything, could still get, well, in this regard, roughly was 9 million something followers, or 900,000 something followers. Well, that was the second part on how can we interpret this. So let's turn to the last part, to the measure of coefficient of determination, not the measure thereof, the coefficient of determination, the r squared. So we're going to use the same table, the expanded table from before, and the coefficient of determination follows this formula. the first value here, that's actually why we needed this additional row, because that's the 180.515 here. That's this value. Then we have minus, both here are the same. That's just the average of y squared, so that's 13 squared. And down here we have the average of y squared. Y squared, that was the row we have here. We didn't yet use this before, now we have to. So here we have the 231.12. That's the average of y squared. So if we insert all of this, looks as follows. That's actually an important aspect. R squared is always between 0 and 1. So this value down here always needs to be smaller than the y squared. If this is not the case, the r squared will be larger than 1 and something will go wrong in the exercise. Also, both of them need to be positive in this regard, because the r squared always is positive. So meaning in the end result you will get something as here 0.1854, which is between 0 and 1. This explains how much of the variance of y, of the dependent, we can explain with the independent variable or with the whole model. So here roughly 18.5%. Is this good or bad? Well, we could turn to the classical threshold values, which tell us if it's below 1%, there's no relation, nothing at all. If it's between 1 and 10%, then there's a weak contribution of the model. If it's between 10 and 25%, that's a decent model, median strength. That's actually what we have here. If it's larger than 25%, that's actually a very strong model. We are explaining quite a severe aspect of what we're studying here. So here, it's a good model. It's not the best of models, but it's still a good model. Well, that was then it about this exercise, which I hope you enjoyed. I say goodbye and see you next time.